Hey everyone, Chang here and welcome to my channel. Today we're going to focus on probability again, except for this time it's a sort of subset, or I guess you could say an approach to probability that we're not entirely familiar with. It's called picture probability. Now here's the thing. We've all heard the saying that a picture is worth 1,000 words. 1,000 may be a stretch, but it is definitely worth more than several words. So for example, this problem right here, I want to say the picture is worth about 25 words, maybe, give or take. All right, so there's a reason we want to focus on picture probability, because there are certain problems where even though you can solve it without using pictures at all, pictures help you better visualize and understand the problem, but it also helps you, narrow down and focus your calculation. So it saves you a lot of computation time. Let's look at this. Given a line segment, XY, so that's the name of our line segment, what is the probability of randomly selecting point on the segment is closer to the midpoint than to the endpoints? So if we wanted to visualize this, what would we do? Well, first and foremost, we would draw a line segment, and I'm just putting these so it's easier to see. Of course, usually it's just points, right? You have your X and Y, that is the name of the line segment. Now, the problem itself is just asking about what's the probability of you selecting some random points on this line segment and it'll be closer to the midpoint. Well, okay, so we got to make sure we have a midpoint there. Let's just say the midpoint's right here, and what a more fitting name than M for midpoint, right? All right, cool. So what's the probability of randomly selecting any point on this line segment and it's going to be closer to the midpoint than it is to the endpoints, which is our X and Y? Well, let's see. How do we really define closer to midpoint? Right? It has to be some sort of distance. So what I'm going to do in this case is I'm going to cut this guy in half right here and this guy in half right here. Now why would I do that? Well, the reason for that is if I pick a random point, I want to say that if it's past this sort of midway between the endpoint and the midpoint, if it's past more of this direction, then yeah, by definition it probably is closer to the midpoint. If it's over in this direction, then it's closer to the endpoint. Same argument for why I'm cutting this in half, right? If it's closer in this direction, then it's closer to the midpoint. If it's closer in this direction, closer to the endpoint, right? So you can do all the crazy calculation you want without a picture, but this picture I think is worth a good chunk of words. It lets us know exactly what we need. We want this entire segment right here versus this entire thing, right? Remember, all possibility is anywhere from your X to Y and anywhere in between. But what we really want is just this section right here, right? Because we want it to be closer to the midpoint than it is to the endpoint. Well, luckily for us, we sort of cut it into 4 equal pieces, right? Because we had this one thing cut in half, so this is technically 2 very large pieces, and then we cut those guys in half too. So these pieces are all equal, right? I don't know what we can call it, one piece, one piece, one piece, and one piece, right? All of these are equal pieces. So if we want anywhere closer to the midpoint than the endpoint, we want it within these 2 ranges. So it's going to be this piece and this piece right here. So out of all of them, if it falls within these 2 pieces out of the total, well, that's what we want. So if it's going to be 2 out of 4 total pieces, which is 1/2, and of course you can always write it as 50% or 0.5 as the probability. And just like that, no real calculation, just looking at the picture and we are immediately understood what the problem's asking and how to find it. Alright, so let's look at this problem right here. Given a target made of 2 circles with radius 7 centimeters and 3 centimeters, what is the probability of throwing a dart that lands between the 2 circles? Now, there's a lot of assumptions being made of this problem, just because this is a basic probability problem, right? First and foremost, the skill of the dart player doesn't really take into consideration, right? If they're super skilled and they're always going to hit bullseye no matter what, then right? This is not the best kind of problem to talk about that situation. The other one is that if they're just drastically poor and they're just always throwing out of bound, then not count either. This one is under the assumption that they will always hit the target no matter what, the quote-unquote target made of the 2 circles. they're not going to hit all the way out of bound, and they basically have no other control otherwise. It's going to randomly hit somewhere in there, right? Equal chance of anywhere on that target. So this one is talking about two circles. We can definitely do calculations without it, but it's just a lot easier to just draw a picture and see it, and then maybe simplify the amount of calculation we really need to do. Well, we're made of two circles. Let's just assume, because from our common sense, our experience, the target's probably going to look something like this. A lovely donut, right? Now, what we want is the probability of the dart landing between the two circles. So we want this area between the two circles. Anything else doesn't matter, okay? So assuming that it's always going to hit somewhere on this target, but we want it just outside. We don't want it to hit bullseye in any way, which is kind of an odd desire, but whatever, right? So in this case, what else do we know? We know that there's the radius 7 centimeters and the radius 3 centimeters. So common sense tells us probably the smaller circle is going to be 3 centimeters and the larger one is going to be 7. Cool. All right, so there we have it. We want to hit between it. So what should we do? Well, they're circles, right? The only thing we really can do with circles is let's just find the area. If we find the area of the large one and we subtract the area of the small one, because those are all the ones we don't want, then we have everything else we want. Simple as that. All right, cool. Well, let's look at this. Area of the large circle. First and foremost, area of a circle equals pi r squared. So if we're talking about the area of the large circle, it's just going to be 7 squared pi, or basically 49 pi, right? Area of the small circle is going to be 3 squared pi, or basically 9 pi. Cool. So if we subtract them, right, we get that little donut area that we really want. So we're just going to have 49 pi minus 9 pi, which is 40 pi. Okay, cool. That gives us the area, but remember, we're not done. This is a probability, so we're looking at the desired area, which is basically this guy right here, that donut shape, out of the entire possibility. And once again, we're assuming that it's always going to hit the target, we just don't know where. The entire probability is the larger circle and everything in it, right? Ignoring the whole, little circle in there, we just want everything in it as the entire probability, or entire possible outcome, I guess you could say. So in that case, we already have that. That's 49 over pi. So in this case, our desired is 40 pi. The total possible is 49 pi. The pi goes away. So technically we have 40 over 49 as our probability for this problem. All right, so let's look at a problem that's actually very similar to the first problem that I ever encountered where picture probability is actually extremely useful, right? I never heard of picture probability before a problem like this, and a problem like this drove me basically bonkers. Once they showed me how to go about approaching this and drawing a picture representation, I thought it was one of the most amazing and time efficient, I guess you could say, skill in relation to probability. So let's look at this for example. Your Uber driver will arrive between 3:45 and 3:50, so anytime in between and including those two. You will be at the waiting point between 3:40 to 3:45. What is the chance you wait less than 3 minutes? So basically, you're going to be arriving there. The Uber driver is going to be arriving there, but you want to see how long you have to wait, right? You want it to be a situation where you don't have to wait anything more than 3 minutes. So what are the chances that you wait less than 3 minutes? Now, there is a way to calculate this without drawing a picture, right? And even if we want to draw a picture, how would we go about it? Now, this is the cool thing about it. Because there's an equal chance in everything, you can actually draw a regular picture representation or a graph representation of the potential of when they're going to come, right? So let's just say, for example, this is the Uber. I guess hard writing sideways. And this is a U. Okay, cool. All right, now let's look at the time possibility. All right, so for the Uber, they start at 3:45. Right, and then there's all the way until 3:50. So let's just go by 1 minute increments. Okay, so for you, you're going to be arriving between 3:40 and 3:45. Now that's the odd thing, but it also makes sense because anything that's not within that time range, doesn't matter, doesn't count, we don't care, right? So of course you're going to start off with 3:40. All right, cool. There it is. That's the time when you will be arriving. Now, imagine I drew this to scale because there's no way I could do it, freehand. My skills are not up to par in any way, shape, or form regarding that, right? Let's just assume that's what we're looking at, okay? Everything else here past, we don't care. Okay, so we're technically just looking at this guy right here. Now, for the time or the chance of it being less than 3 minutes, it's basically, well, let's see. It has to start where? It has to start about right here, right? If you arrive at 3:42 and the Uber arrives at 3:45, then basically that's 3 minutes. And of course, if you arrive at 3:43, the Uber arrived at 3:46, it's still 3 minutes. So we're looking at basically, what else? 44, this is about 3 minutes. And 45, this is about 3 minutes. Okay, cool. And so if we draw this right here, what we really want is all of this time right here. Okay, we don't want anything else. Well, if that's the case, notice that this is basically a nice, what is that? 1, 2, 3, 4, 5. 5 by 5 grid, right? 1, 2, 3, 4, 5. Just double checking. 5 by 5 grid. All right, cool. So this is a 5 by 5 grid. Imagine that there's a equal probability of you arriving anywhere on this time, Uber arriving anywhere on this time, but this is what we want right here. Well, if that's the case, let's just look at this. This looks like a poorly drawn triangle, but a triangle nonetheless. So if we look at the area of a triangle, that's 1/2 base times height. Okay, our base is 1, 2, 3. Our height is 1, 2, 3, and we're going to do 1/2 of that. So that's going to be 1/2 times 3 times 3, which is 4.5. Okay, all right, cool. So that's the area of the triangle. Well, the area of the whole thing of a 5 by 5 grid, area basically of a square, is just base times height, which is just 5 times 5. That gives us 25. So what's our probability? Well, the probability that we want, right, where we are going to meet each other less than 5 minutes is going to be 45 over 25. And now that looks really weird. Let's just say that's what? 9 over 50, or even better, let's just say that's 18 over 100. So basically 18%. Or 0.18, your choice. 1/8, there you go. All right, cool. So look at this. A problem that starts off with something that's not great. I'm not sure how to go about calculating it until drawing a picture and just realizing that we can calculate the probability just based on the area, right? Because equal chance of it arriving in anywhere of this is all equal weight. We have our desired area versus the total area, and that gives us our probability for a problem like this. All right, so there you have it. Picture probability. Now, this is a skill. This is not a new topic. It is not some crazy new, I guess you could say, genre of probability, just a skill. All it is that there are certain problems where it might just be a lot easier to represent them in pictures. And when you can represent them in picture, make sure that the picture makes sense. But when you do that, it saves you comprehension, I guess you could say bandwidth, right? Because if you're trying to comprehend it and visualize it without actually seeing the picture, it might be a little more difficult. You might waste a lot more time on it. But also, after you draw it out, right, it focuses you on what exactly the math is. Like the previous problem, the focus immediately we knew is on area. This one, the focus we immediately knew is also on area, but it's on relation to triangles and square, whereas the other one is circles, right? That saves us a bunch of calculation instead of trying to break this down into some complicated way and then trying to make sure that, I don't know, verify that the probability is correct. We can actually just see it, conceptually understand it, and then calculate it, right? Hopefully this skill is useful. It doesn't work on all problems, but if it does, it is one zinger of a skill that will save you a lot of time, a lot of mental bandwidth, and makes you feel like a boss. All right, thank you for watching this video. Please like, comment, and subscribe. I will see you in the next one.